All right, so the title of this talk is Fuzzing Sucks. And really the purpose of this talk is to introduce a fuzzing framework that we've had for some time and that we've decided to kind of wrap up, document, and put out there. Because we feel, at least, it does a lot better of a job in the open source fuzzing world than any of the current existing tools. So just a quick slide about us. We both work at Tipping Point. We work for the security division called Digital Vaccine Labs. And in our specific group, we're responsible for vuln dev, patch analysis, pen testing. So in the product assessment that we do, that's why we've had to kind of build this fuzzer. So when we're testing like our VoIP systems, and 3Com is our parent company, for those of you who don't know, these are the kind of products that we look at. If you're interested in keeping tabs at us, the advisors that we find, blog entries, all that kind of jazz, you can go to dvlabs.tippingpoint.com. Other things about us, I launched OpenRC. It's a reverse engineering community over 2 years ago. And just quick curiosity, show of hands, how many people in here are members? More so than the other talk that Cody asked about. But so if you guys are interested in reverse engineering, this is a good community site. It's got blogs. A lot of the guys who you hear doing reverse engineering stuff, they keep some materials here, so it's a good place to kind of go to. And we have some interesting updates coming after Black Hat for OpenRC. Arrow and I are going to be working on some like service-based things where you'll be able to like connect your IDA database to OpenRCE, and some work will get done to your IDA database, so you can like publish scripts and tools without actually having to reveal your source code if you're interested in doing that. Other things we've done is we've created the PyMay RE framework. Who's heard of that? Just out of curiosity. So a lot more of you guys. How do you guys hear about PyMay but not OpenRCE? They're like hand in hand. Huh? And again, also in that one, after Black Hat, we're going to be refocusing our efforts on PyMay. Cameron, who's in the audience here somewhere, has been working on a SQL backend. So there's a lot of updates to that's going to be coming out. And finally, the last piece of probably the most relevant information is I just finished co-authoring a book with Michael Sutton and Adam Green, who are floating around as well on fuzzing. And, it all kind of goes hand in hand. So talk outline. First of all, what the hell is Sully? Sully was named after that Monsters, Inc. creature that you see over there. It was actually Aaron's idea for the name. I can't take credit for it. But it's a pretty creative name. And it comes in handy later on since it both starts with S, just like Spike. And it'll make sense in like 5 minutes why that matters. So what we're going to be talking about, first we're going to start off, why does fuzzing suck? What are the pain points? And, what can we do to make it better? And specifically, what does Sully do to kind of address these pain points? Then we're going to go into the Sully architecture. So the component breakdown, how it's designed, if you want to extend it, where would you look? And how you would actually write a fuzzer on top of this framework. Then we're going to do 2 example walkthroughs. So we have a Trend demo and a Hewlett-Packard demo. And both of them unveil bugs that haven't been fixed yet. So, bear that in mind when you're... No photos allowed of the source code when you're looking at that. And finally, we're going to talk about the future development. What's still on the drawing board? What can you do to help to kind of extend the framework? What we're looking to, glean from other people. And before I even start, I have to address this InfoSec sellout blog posting. I don't know who's familiar with this. The site's since been taken down. But sometime before Black Hat, they just kind of had like a review of the Black Hat talks going to be going up there, and they refer to fuzzing as a dead horse. And so my retaliation to this is that I don't think it's a dead horse. We've got an entire Black Hat track dedicated to this year. There's 3 dedicated books. I just heard of a 4th one coming out. There's more commercial vendors popping out in fuzzing than there ever was before. And it's still highly effective. Like, you write a fuzzer, chances are you're going to be finding a bug in whatever target you're looking at. So, summation, fuzzing is not a dead horse. So some past and present on the fuzzers that existed and the fuzzers that exist now. Old school, you have things like anti-parser, defuzz. These are lesser-known fuzzers. Spike is obviously almost a household name at this point. That David Tell wrote that one. He's over at Immunity. It's C, Unix, block-based. And this block-based is going to come into play later on. It's the same way that we approach data generation. And this list goes on. There's so many of them. I want to say there's like 50 fuzzers out there. Angel, Spike File, Art of Fuzzing, Fuzzy Packet. This is just an example of a defuzz, defuzz FTP fuzzer. It's a custom language, so it's a DSL domain-specific language versus just exposing the API. And you can see it's pretty easy to understand, but you're going to hit the limitations on this really quickly. So this is a very simple FTP fuzzer. You specify the peer, read, the write, what kind of data you want to put in there, and it'll fuzz it for you. Here's an example of Spike, how it does data representation. And this syntax is really simple, and perhaps why this is the most commonly used fuzzer. And we're going to get into how we do our data representation later. The new wave of fuzzers, you've got Peach, which is really elegant. When I saw Peach, this is probably the first fuzzer that excited me. I thought, oh, what a cool a way of approaching it. It's highly modularized. He kind of separates the data generation from the data transport, from the data transformations. There's Codenomicon, which is a commercial vendor. You can't really build your own fuzzers on this. They write their fuzzers, they pre-generate test cases, and then they'll give you a Java tool that's capable of replaying these things. So if you buy the SIP fuzzer from Codenomicon, you'll get a tool capable of producing 50,000 test cases. And so this is one of the first motivations behind us creating our own fuzzer was when we bought Codenomicon to test our VoIP products. No offense to the Codenomicon guys, those guys are very smart. I'm in touch with one of them, but their product is still kind of catching up in terms of usability. So what we end up actually doing is Cody, one of the guys on my team, they have an HTML representation for every one of their test cases. He wrote a parser to pull out all their test cases so we could write our own harness to use it because we just could not use a Codenomicon fuzzer in any way that was usable. So we call it now Codenomicon. And it's, it will work with any future version of Codenomicon. It's just like a testing harness that will wrap around their test cases. There's GPF, which is written by Jared DeMott. He spoke earlier on EFS, which is an evolutionary fuzzer. There's Autodaf. For those of you who don't know, but it's really interesting. This is kind of a next generation of Spike. It's essentially Spike with a debugger functionality built in. And I want to say that this is the first fuzzer that actually incorporates, or the first network protocol fuzzer that actually incorporates a built-in debugger. And what they do with it is they're not really using it for fault detection as much. They're using it for what they call this markers technique. So every time that you send data, if it sees that data is going over a string copy or other potentially dangerous API call, it's going to give more weight to that test case and fuzz that more because it's thinking, okay, there's a better chance of this causing a security vulnerability than, say some other test case that's going over what's considered a safe API. In the evolutionary fuzzer world, you've got Sidewinder. That was presented last year at Black Hat. Sherry Sparks. They never actually put out a released version of it yet, but it showed a lot of promise. And Jared, I haven't gotten a chance to check out his yet. And unfortunately, I couldn't even make his talk because we just finished the slides 6 minutes ago. So I haven't seen that yet either. And the last thing I mentioned is the Protocol Informatics Framework. And this is work that was done by Marshall Badeau over at, that's Mu, right? Yes? Mu? Yeah. So anyway, he's over at Mu. It's not really a fuzzer, but it's worth mentioning because it is really new age and kind of helps fuzzing. He applies bioinformatics to kind of look at data streams and separate out into protocol fields automatically. So really interesting work, kind of stuck in the research phase. I don't think anything was ever fully released out of it, and I'm pretty sure that those algorithms are being used at Mu now. Here's an example of Peach. Peach is written in pure Python. It doesn't use a domain-specific language, it just exposes an API. And the thing with Peach, unfortunately, is it's non-trivial to learn how to use this fuzzer. I'm not a dumb guy, and in the time that it took me to kind of really get a feel for how to master Peach, I probably could have rewritten Peach. So it's just not an easy thing to work with. But it is definitely a powerful fuzzer. GPF has an easier to use data representation format. The one negative aspect of GPF is that it has extremely unwieldy command lines. I don't even know if you can see this thing down here, but that is a long-ass command line, which I'm pretty sure even Jared could not decipher at this point in time. So pain points and solutions, Aaron can kind of walk you through.
Yeah, we're just going to go over a few of the things Pedram already mentioned with the different frameworks and why they're lacking, or why we think that they're lacking, and what we did to improve upon them. Pedram mentioned his book previously. Chapter 5 of that is going to cover basically the things that we're going to go through here. I'm going to go through each of the different advantages, disadvantages to the fuzzing frameworks that are out there, what we do, and we're going to drill down into our architecture and what specifically we do to remedy those. So the first thing we're going to go through is the learning curve that Pedram just mentioned with, say, Peach Fuzz. It takes you a while to get a hold of everything. And the simpler ones, you'll reach the limitations really quickly because they're solely based on data generation. So you're not going to really be able to do much. You're not going to have the debugger aspect. You're not going to be able to do much else other than just generate simple data. You're not going to have any context in the communication protocol that you're dealing with. It's just going to be simply generate this data, send it over the wire. With Sully, what we did is we kind of took the block-based approach that Spike takes. So you're declaring all of your all the aspects of the protocol in block form. It's very simple. It's Python, so we took advantage of that, and we have keyword arguments. So, for instance, if you want to represent an integer, you can say Sully integer and give it the default value. As you start to use Sully more often, you're going to be able to use all the advanced features where you have keyword arguments like, fuzz the entire range of this entire integer, everything you can do there. The endianness, switch this, switch that. There's a bunch of different things that you don't need to use right away, but as you start to get used to the framework, you can use. Also, because it's in Python, we have access to all the libraries that Python itself has. So things like zlib compression, you can just import that and use it, and it can be part of your fuzzer. The other aspect of ours is it's very modular. So you have all the different components. You can farm out to your team. Specifically, that's very useful for our team. You can farm out different parts of the protocol, say there's this custom structure data type that they're using. You can farm that out to one member of the team while somebody else works on everything else. And it's very easy to put all those together at the very end to have a complete fuzzer request working. The last thing that we have on here is things like challenge response and previous packet determines the length of the next packet and things like that. Our fuzzer is context-aware, session-aware, so you can have a complete state of the protocol defined, and you can handle all sorts of things like challenge response. The next pain point we have is being able to reproduce any problems that a fuzzer does unearth, and being able to document such things. Most of the frameworks out there don't actually do that. They'll just generate the data, then send it over, wait and see if there's a crash. And you can't really go through and see all the context data with any kind of crashes that may occur. Another thing we do is we have a HTTP server that's bundled with our framework that is automatically refreshing and showing you which fuzz case you're on. You can look at the PCAP for that particular fuzz case. You can see how far into the entire mutation index that you are, certain things like that. You can replay any of the PCAPs that you do have. So, for instance, if our fuzzer tells you that test case 216 caused a crash, you can just replay that PCAP, and you should have the identical situation. Reusability is our next slide, which is basically the thing about Sully is when you create a specific request for some kind of protocol you're dealing with, you're going to save it to our library. So the more that you use Sully, the larger it's going to get, the more smart that it's going to get. So if you're dealing with specific software that uses similar protocols, you can kind of just pull out requests that you've already generated and just use those. So you don't have to create complex types and data types and different structures that specific protocols might have when you can just pull them out of the library.
We talk about this later. We call it Legos. But like, for example, if you want to fuzz an email address, an email address shows up all the time. So once you've created a complex type for an email address, you never have to do that again. It's in the library, and now you can just say, okay, here's an email address in the protocol. I don't need to re-say that it's a string with a delimiter with another string, et cetera, et cetera.
And we have examples of that, email addresses, IP addresses, all that kind of stuff. So the next part we have is being able to basically understand the state of a communication. So if you have a protocol that has decision trees in it, so there's two different paths that the communication could go down, we can basically fuzz each one of those individually. So we store everything as a graph, and you can build your requests, which is going to be the entire fuzz file itself, and the request is going to be a bunch of sessions tied together, essentially. So you can fuzz every single down graph of a specific graph that you're dealing with. If you want to go, for SMTP, for instance, it does, the hello verb or the EHLL verb, and you can fuzz any protocol that has certain decisions like that may or may not be the same. We walk down every path and do every single one individually. Okay. The other thing that we have is code coverage. We are in process because we're utilizing PyDebug, so we're actually attached to the process that you're dealing with. So we can do things like code coverage. And most fuzzers out there, they don't actually do anything like that. So you could be sending 500 test cases that go down the exact same path, which is fairly useless, whereas we can tell you when you're going to be splitting off from that path, why you split off from that path, which primitive was being fuzzed at the time that you did split off of that path, so you can kind of have a better idea of the protocol without having to reverse the whole thing out. We use PyMay for that, which does regular. You can do stepping step-by-step instructions, or you can do MSR-based code coverage, which is just basic block by basic block. And because we're in process, we can do things like detect access violations, detect null pointer dereferences. We can do a bunch of things like that. Most of the fuzzers out there, like Codenomicon, it'll generate the data, send it over, and, well, you have no idea if something bad actually did happen. You just kind of wait and hope. Different approach like Mu and Breaking Point is they'll just cycle the device that they're actually fuzzing. So if they're fuzzing a switch or a router or something like that and it stops responding, they can actually just completely cut the power and start it back up. So we have something similar to that. Because we have a process monitor attached and we're using PyDebug, we can catch any exception that occurs, figure out what type of exception it is, dump context data, tell you, I mean, it's very easy at a glance to tell if something is going to be a null pointer deref or something that's going to be more interesting than that. We dump the SEH chain, all sorts of things like that. And if a crash does occur, we have another concept of, well, we have the process monitor itself is what we call an agent. And we have a few of those. Another one is the VM control agent. And that one monitors the VMware instance that you're running, if you're running it in that situation, so that if the process monitor agent detects a fault, it notifies the VMware agent, which can reset to a snapshot where things are running okay, which we're going to demo later. Another problem with a lot of the fuzzers out there are going to be the amount of time it takes to actually understand the protocol, get your fuzzer written, and just get to work on it. So we have a few utilities that remedy that, like a PDML parser. PDML is a packet descriptor meta language, I think. And it's a format that Wireshark and other sniffers can output sniff data to. So it's just an XML format, and we have a little parser that will just run through that and give you all the Sully primitives and a complete request that you're going to have to probably go through by hand and trim a little bit, but it'll save you a lot of time. Because Sully is very modularized, you can have many people working on different aspects of it at the same time. Yeah, so it's definitely just, we have a few utilities, obviously, for doing that kind of stuff. It just makes it a lot easier than the current things that are out there. Now we're going to go into architecture. Pedram's going to cover that.
So this massive diagram seems a lot more complicated than it really is, and we're going to kind of zoom into the different portions to describe what everything does. But in essence, this is like the high-level overview of how Sully works, how it's all the components, how it's made up. So this gray shaded area where it says user developed, if you're building a fuzzer, that's really all you have to worry about, is that small portion of it. The rest of it is if you want to actually extend the framework, creating a new agent, writing new utilities, whatever. So we have this data generation piece. We've got these primitives that we're going to walk through, and Legos, which are our word for custom-built complex types. We've got blocks, and we have utilities, so stored encoders, and all the stuff we'll get into. And from there, these all go into a request library. So you will write a request, store it in the library, and then pull them together in a script that you're going to write called a driver. That's when you build this graph relationship between these requests. The session management component is what's actually going to walk this graph and do all the fuzzing for you. The file system is where the crash bins, packet captures, session data gets stored to. We've got command line utilities that are kind of like their own little piece, and various agents that are responsible for instrumentation, monitoring, things of that nature. And then I've got this little HTTP icon to kind of demonstrate that your driver, because it uses the session class, has this built-in web interface. So there's these four major components, right? You build these requests out of primitives and Legos. You have these requests chained together in a session. You tie them all together, targets, agents, and requests in a driver. And like all these words in red are our Sully speak. They all kind of make sense, but they're highlighted just so you know what the variables and functions will be called. So general usage, how would you use this, outside of this talk? You don't care about how it works. You just want to use a fuzzer. And it's pretty simple. You sniff some traffic or you verse a protocol, and you break it down to these individual requests. So in the case of SMTP, which I'll be using again later, you might have a hello request, a mail from request, a recipient to request. You represent all these in this block format, tie them together in a session, and then just say fuzz and review the results. The rest of it is all automated and taken care of for you. So drilling down to this graph, this data generation piece, with the overview, Attell really had it right. His block-based approach for protocol representation is really simple. It's extremely powerful. You can pretty much represent everything or any individual request in this block-based format. The kind of things you can't do, like deal with challenge response and what we call previous packet specify size, those are taken care of in the session layer. And so, these protocols that you represent as primitives, blocks and block helpers, they all have these optional arguments. And for example, one of them that's common across the board is the name optional argument. This is going to give you direct access to a primitive instead of having to walk the block stack to get to it. And you can see, this is probably a good time as any to kind of pull up the Epidoc documentation. But we have these docs. It's pretty extensive. It comes with it. It's just to kind of prove to you that we spend a lot of time documenting. It's going to be a good read. And then, of course, you've got the Epidoc generated stuff. So if you want to know, for example, what optional arguments a certain primitive takes, it's really easy to do that. Come to primitives. I want to look at, whatever, a group. And then you can come down here and see all the arguments, optional arguments, and the kind of helper text that you've written. And finally, every request is going to start off with sinitialize. And we're going to start stepping through the different API that you're going to be calling to build out these requests. So static.
All right, so I'm going to go through some of the actual primitives, which are the simplest types that you're going to be using to define the requests you're dealing with. First one we're going to go through is static, which is pretty self-explanatory. It has aliases, deno, raw, unknown, things like that. And you basically can give it just a string of whatever static data you want. Binary we kind of took away from Spike, which is you can do similar things, but you can represent the data in all sorts of different forms, as you can see up there. Another one we have is the random primitive. The random primitive is the only one that doesn't have a set library of values. It is actually done heuristically, so it generates random data every time you're going to instantiate it. And you have different arguments to control how it's going to do that, the minimum length, the maximum length, the actual number of mutations that you want to deal with, and things like that.
I got it. Integer primitives, simple fields for like a character, a short, long, D words. And there's convenience aliases just like with the sdeno, s unknown. And so, like he mentioned, all of our primitives are based off of a fuzz library, a set of heuristical values just chosen that may cause a fault. So one of the optional arguments for an integer is that you can turn on full range, where it'll go, for example, in a short, it'll go through all 65,000 plus options. So let me pull up the source code real quick. Here it is, primitives. All right, let me pull up int. All right. So for example, anytime you instantiate an integer, we're not going to cycle through every single value by default, because that's going to, the combinatorial explosion that's going to occur there is just going to take forever for your fuzzer to finish. You can turn it on if you want, but by default, we try and keep things, same values. And so here are the kind of the areas that we choose. We're choosing integer boundaries that might be interesting. So 0 and max known are obviously interesting boundaries for any size integer. Or divided by 2, divided by 3, divided by 4. And this add integer boundary is going to do plus and minus 10 from each one of those sections. So if you have something like a heap allocation that's going to occur off of a integer field in a protocol, and the math on that's going to be like a +1, we'll catch that wrap. Or if it's going to be like, times 8, because that's the size of some structure of +5, we'll catch that as well. So it's just some integer heuristics to put in there so that you don't have to go through this full range of values to fuzz. Other things you can do with the integer primitive, it supports ASCII, so if you're doing like a content length in a HTTP post, you can render it ASCII. Or if you want to render as binary, you can render as binary. You can do signed or unsigned. They'll throw a negative sign in there in the case of ASCII.
So the next one we have is the string primitive. The string has all sorts of different options that you can have, static sizings, paddings, all sorts of things like that. It also has a fuzz library similar to integers, which I'll pull up in a sec. Another thing that we have are delimiters. So we have strings, which is just, you're going to give it a default value. That's the only thing that's required. After that, it's going to go through the fuzz library and just linearly replace with all the different values that we have. I'm going to pull that up now. And you can see we'll take the actual value that you provide as a default value, repeat that a certain amount of times. We'll do things for UTF specifics. We'll do things for format strings. Just a lot of different things that we've encountered that will cause problems. We've ripped examples from Codenomicon, from Spike, things like that. All sorts of different problematic strings, basically. So we have a little example here, which is just going to show an HTML tag. The first thing that we start with is a delimiter. So delimiters are basically like strings, except that we have specific ways that we're going to mutate those. Sometimes we'll just take out the delimiter. Sometimes we'll do directory traversal kind of things. We'll do a lot of white space, all the different problems that generally arise from delimiters themselves. So in this example, we declared delimiter, which is just a bracket a string for body, and you can see it's just an HTML tag basically, comprised just of strings and delimiters.
Blocks, so this is where you take all these basic primitives and you put them in blocks, and you nest blocks, and this is how you really build a complex protocol. So if you're familiar with Spike, this is very similar to you. If you're not, this is new stuff. So we can take a block, instantiate one, and just put whatever primitives we want in there. And blocks are opened with sBlockStart, closed with sBlockEnd, and both these functions return true by default. So in Python, if you want to just tab it out so it looks nice, you can do that. And then what you can do with blocks is you can associate them with a group, an encoder, a dependency. And these are some of the more advanced features of our data representation that kind of takes it above and beyond what Spike and others could do. So if you have like a scale of 1 to 10 of like shitty fuzzer or perfect fuzzer, maybe in the data generation world, the current fuzzing technologists take it to like, I don't know, a 5 or a 6. And so we're hoping that Sully takes it to like a 7 or an 8. But on the other aspect of the world where it's like monitoring, automation, the other portions of fuzzers, maybe the fuzzers available today take it to like a 1, and we're hoping that we'll shoot that up to like a 5 or a 6.
So the next part we're going to talk about is groups, which is another similar thing to primitives. A group is basically going to be a list of specific values that you want. The example we use here is HTTP verbs. So if you're doing get, head, post, trace, things like that, you can actually create a block and have it start with a group, and that group is going to iterate through each one of those things. So, for instance, if you have a block that has 2 strings, it's going to have the number of mutations that a string has is about 1,000 in our fuzz library. So you multiply that by 2, and your block itself has 2,000 different mutations. So if you're going to prepend that with a group, such as a get, head, or in our example, we're using get, head, post, trace. That's 4 different verbs. So the amount of mutations you just basically multiply it by the number of items in the group. So 2,000 times 4 is going to give you the amount of mutations that specific block has. So it'll change it, mutate everything within it, finish that mutation, and then go to the next in the group and continue in that fashion.
An encoder is a really simple concept, but it's extremely powerful. And an encoder is how we actually do things like if you want to fuzz DC RPC, or Ganesh, who's talking at DEF CON, if you want to fuzz SCADA even, DMP3 protocol, like you can do that with Sully because of this simple concept, which really adds a lot of power. So all it is a block modifier. And what we're doing is we're going to connect a function to any given block. And so when that block is finished rendering, it's mutated, it's rendered as contents, those contents then go through this extra channel, through this function that you add, and that's what actually goes out onto the wire. So you can represent your data normally, and then if it's, for example, zlib compressed, you just attach one encoder to it, and it will generate the protocol, validly. And so in the case I give here, this is a real-world example. It's not the trend demo I'm going to give. It's another trend target. But for this protocol, they used a custom XOR encoding routine for all of the packets on the wire. So I reversed that out, and then I created an encoder. So now I can just draw out the protocol using the basic blocks and not have to worry about how it's encoded. At the end, I just tie this function to my data, and it's all taken care of.
We also have this concept of dependencies. This originally stemmed from this fuzzing framework a long time ago, about a year ago actually, was an attempt to fuzz SWF files. And SWF, that file format, is a pain in the ass because it has dependencies all over the place. So after scrapping that framework and starting up on this one, we did keep the dependency aspect of it, which is basically, in this case, what we're going to do is you're going to have, we declare an opcode, which is a short value. So then we declare a block after that. And in certain cases, we're going to want that block to be rendered. Say, for instance, if the opcode above that, during mutations, if that opcode is a 10, if that's what the render value is, then we're going to want to render that block with the string Aaron right there. For instance, if it's a 15 or 16, we would like to render the next one, which is a URL, and the next one is if it's not 10, 15, or 16. So the arguments that you can pass to a block like this, if you're dealing with dependencies, are you give it the dependency primitive, so that's the dep equals opcode. Then you give it the values, so dep values is 10, 15, or 16. And the comparison, so that is actually something that's going to be evaluated. For in this case, it's not equals. You can do equals, you can do less than, greater than, things like that. So at any given point, only one of these blocks is going to be rendered, and that depends on the value of the short opcode. This is very useful for certain protocols.
This concept of sizers, again, this is something that is necessary for doing block rendering. It's one of the things that Spike kind of introduced. So you apply a sizer to a block, and it dynamically calculates the size of that block. So if you have a protocol that's going to be like a TLV, you have a type, you have a length, and a value. As we're changing that value, as we're cycling through the different options for that value, we want that length to be updated so that the actual parsing of that TLV is correct, but then maybe in the parsing of that value later on down the line is where a fault is induced. And so by default, you don't fuzz a sizer. You want these sizers to be valid. But of course, you can turn this on as well. You can fuzz a sizer just as if it was an integer. And so we can do things like specify the length. I want to say it's a 4-byte length of this block. The endianness, again, the output format, binary, ASCII, whether or not it should include itself in the size count. And all this will kind of become clear when we pull up some real samples.
Yeah, basically, all these different representations are just to make it so you can take a complex protocol and very quickly and very easily represent it. Another thing that we do is checksums, which allow you to, this is very common in protocols, obviously, is just to throw a checksum for a certain block. So you associate a block, you say, I need the checksum, you point it at that block, it'll calculate the checksum and append it or prepend it, depending on where you put the checksum. You can give it an algorithm for CRC32, Adler, MD5, SHA-1, or any arbitrary function pointer, meaning you can actually define your own checksum routine and just point it to that function. You can do things like tog the endianness of that representation and other things.
Another concept also new to this framework, kind of advancing data generation, is the usage of repeaters. So if we have a block, we can use an sRepeat instruction to repeat that block a variable number of times. We can do from min to max, how often, how much is step it per iteration. And alternatively, we can tie it to a variable. So repeat this the number of times specified in some other integer that's being fuzzed. So if that integer goes up to 20, repeat this block 20 times. And this is useful, for example, there's been a couple of bugs in like a Microsoft Excel where the issue hasn't been in the parsing of like a single table entry, but if you had too many entries in a table. So if you have, in this case that I give, a table entry of the form type length string, and I'm creating a block here, I just call it table entry. I've got a random, I've got a size. You can see this size is length 2 and it describes the length of this next block that's being defined. That one just contains a simple string. And on the bottom, we're going to repeat it from 100 to 1,000, stepping at 50 every time. So if there was an issue with parsing too many entries in the table, we can represent that in this data representation format, which you couldn't do before.
So all the things we just previously went over are things that are currently built into the framework. This new thing is the one part where we start to get into the extensibility of the framework. We call this Legos, and it's basically allows the user to create complex types of their own definition. So email address, IP addresses, or whatever particular data structure that the protocol you're dealing with might itself define. So this is basically a library of data types that you can extend that Sully itself has. This example right here is creating a Lego called tag. So this could be XML tags, HTML tags, whatever other kind of tags are represented like this. This looks a little bit, it's not quite as easy to read as everything else because this is the part where you may be extending the actual framework itself. Using the framework is you don't have to really deal with this stuff, but you can see that we're calling push a few times, and that's actually pushing onto a stack that represents this data type. So first thing we're pushing is a delimiter, which is a bracket, and then a string, which would be the contents of that tag itself, and then an ending bracket. So that's a very generic way of representing a tag, and then in any future request that you're dealing with, you can just import Legos and import this tag specifically and use it for whatever you need, and Sully will take care of the fuzzing for it.
So like some of the Legos we have are like ASN1 types, email address, DNS host names, URLs, just things that you're going to be seeing frequently all over the place. And one of the ones we have that we broke last week is an IP address Lego, where depending on your testing environment, it'll update the IP address to either the client or the server. So if you're dealing with a protocol where the actual IP address of either the source or the destination is embedded in the protocol, it'll auto-update, and it'll fuzz it as well as this dotted quad or binary format. So that's the data generation piece. The next piece of it is this whole session management concept. So first, an introduction to pgraph. Pgraph is just a Python graph abstraction library, and I originally wrote it for PyMay. It's just really easy to use. You launch Python, you say, okay, here's a node, connect these edges together, and you can render it in any of 3 different languages. You can do GML, GraphViz, and UDraw. And the session class extends from this, and this is how we do This is how we do this graph-based approach of building a fuzzer. Every request that we build is a node, and then we tie them together in a graph called a session. So one of the things you can do, I have a graph of this? Yeah. So we can register pre- and post-send callbacks to the graph. We can assign a callback to each edge. We can add multiple network targets in the session class. This is where we expose a custom web interface. We communicate with registered agents. And this is the class that's responsible for walking the graph structure and fuzzing at each level. And this is very tightly used in creation of drivers, which we'll give an example. So this concept of like graph-based protocol representation is what gives us a lot of the powerful features. So in this example, I give, it's SMTP again. I promised I'd bring this up. So here's like the root node where you can define a pre-send. So before I send anything, you can define a function to set the session up. So if I'm fuzzing DC RPC, I'm going to do an RPC bind. And that's an example I'm going to show in the trend. And then we've got a decision branch. We can either start off with an EHLO or a hello. Then we've got the mail from request, recipient to request, data request, and we have an optional post send as well. So if I'm managing the construction of a fuzzer, I can say, Aaron, I want you to really research the hell out of and write a mail from request. Cody, I want you to go and look at hello and EHLO and create requests for those. And they can go off and do their own research and come back, and we can tie it all together and do this full case fuzz. So for example, let's say we have a system where it's a challenge response, where we send out a packet with a challenge, we get a response back, and we need to use that response in the next packet, the next request. What we can do is we can define a callback function and assign it to the edge between the challenge response mechanism. And what that callback is going to get is it's going to get the next request that's going to go out, the request that just went out, and the packet data that came back and forth. So you can parse it, pull it out, and assign it into your next request, and essentially handle challenge response, previous packet specifies next length. And this is something that you could not do in other frameworks that you can do now. I remember Charlie Miller, who deserves huge kudos for really being a key editor on our book. Him and I were kind of going back and forth on the pain points of fuzzing, and this was before I had shown him this, and it was kind of uplifting for me to hear from him saying, "Oh, that's cool! I can't believe you thought about this, X, Y, Z, 1, 2, 3. I'm excited to start using this thing." Another thing to mention here is, I forget what bug it was, but it was an Ipswitch where there was an overflow in the parsing of email addresses with a certain form in, I think, mail from. But depending on whether or not you came in from an EHLO or an HELO, it would or would not show itself. So the bug was only if you went down one path versus another. And so the benefit of doing things like this is we can create these arbitrarily complex protocols, and the fuzzer takes care of it all for us. Every path, every node is going to be fuzzed individually. So it would start off, for example, and it would go through every iteration of EHLO. When that's done, it's going to revert it back to the valid form that you gave it. Then it's going to send pre-send, valid, and then start fuzzing mail from. When that's done, it'll go pre-send, valid, fuzz, recipient to, all the way through to the end. And then it'll go the other way around, pre-send, fuzz, pre-send, valid, fuzz, and give you every single path, every single request. This is a screenshot, and you'll see the real version of it, of the web interface. It's really simple and bare bones. It's going to tell you what's our total progress, what's the progress of the current request. It's going to give you a list of all the crashes or the faults that were detected. If you click on this link, it'll pull up the actual crash dump. On the right-hand side, which is cut off in the screenshot, is a link to the PCAP. So if you want to just pull up the PCAP to take a look at it, you can do that as well. You can pause and resume the fuzzing. And actually, because our session has a built-in state saving to disk, you can stop fuzzing, shut everything down, and then start it up a week later, and it'll pick up right where it left off. The next piece that we're going to kind of zoom in on and explain is the agents piece.
So agents are another extensible part of the framework. Right now we have a few defined. Basically what they are little programs that communicate over what we call PET-RPC, which is just a way to remotely call any of the functions, just a simple form of RPC. I'm going to go over a few of the ones that we've developed so far. The first one is we call netmon. This can be run either on the same machine that you're fuzzing from or on the target system. And what it does is it uses PCAPI and IMPacket to save all the packets in every single test case bidirectional to disk. It allows you to do BPF filters, so you can say, source or desc port this, and it'll just save everything. Depending on the log level, you can have it, print more debugging output and things like that. The next one we have is our process monitor. This one is probably the most interesting. It is a PyDebug-based agent that you run on the same system that that the target software is on, and it'll attach and it monitors the health of the actual process. So while you're fuzzing, if an access violation occurs, this will dump all context data. It will save it in what we call a crash bin, which is just a marshaled data format, which will save all the context data. It'll save the current instruction. It'll save the SEH stack, all that kind of stuff. And there's a lot of other things that you can do with this agent because it's written in PyDebug, which is written in Python, which is scriptable. You can do all sorts of different things in this one. The next agent that we have is the VM control. This one is generally going to be run from the system you're fuzzing from, and it allows you to revert the VMware image to a known good state. So if a access violation occurs, the process monitor, which is attached to the process, notifies the VM control. The VM control will reset it to a known good state. Meanwhile, you're going to have the saved PCAPs, you're going to have the saved crash bins, and the web interface is going to be updated, showing you all that and having links to all the information you would need. This one's pretty straightforward. It has an interactive mode that we recently added that just lets you basically just say VM control -I, point it to your VM run, point it to your VMX, and you're ready to go. And Pedram's going to go over the drivers now.
So the driver is really where it all comes together. You take your requests out of the library, you instantiate a session, you instantiate some targets, you describe them, you connect it to agents. This is where you define your pre and post sends. And it's really free form, though most of them will follow the same structure. And we're going to talk about how, or later in the future development, we're going to attempt to make a GUI around this. So here's an example driver. I'll zoom in. And actually, this is the driver that was used to discover a fault in Trillion in its Jabber protocol parsing, which has now been fixed. But so here's kind of the bottom of it, right? We have this new session being defined. I'm specifying the file name to store the session information to. I'm instantiating a new target. So this is the IP address and the port that we're going to be fuzzing. And then we have, I'm creating 3 agents. I'm saying the netmon, procmon, and VM control. Here's the host that they're at and the ports that they're listening on. Those are all default values, the 26,000. Then we are starting up the target. So I'm saying target.vmcontrol.restart target. So it's actually going to bring up this virtual machine where I've previously saved or taken a snapshot, running a snapshot. I'm adding the target to the session. I'm saying before you fuzz anything, you've got to send this pre-send init message. This is where I'm doing the actual graph. In this case, it's a single request, so there is there's not multiple nodes. And I'm saying connect the root node to sget is going to pull the request chat message out of the library, which I've defined earlier, and then just session.fuzz. At the top, you'll see we're importing Sully from the request library, we're importing Jabber, and here's the function that was defined to do the initialization. All it does is it's going to send this very simple XML packet, because you can't begin to communicate with Trillion Jabber unless you send this initialization vector. So I didn't want to fuzz this, so I just made this a static, do this before you start fuzzing the next request. So fairly simple, fairly straightforward. The next thing is these command line utilities. And since we're somewhat might be getting tight on time, let me do this Crashbin Explorer demo real quick. So the Crashbin Explorer is what you use as a command line utility to actually explore the Crashbin that, to save. So I'll go into this utils directory, and I've got this Crashbin Explorer. So I'm going to give it a path to, for example, our saved Trillion audit. Why is that? Archive fuzzies? Yeah, that's for stuff that you've finished. Man, I can't see it on the screen. Hold on one second. All right. So this is the actual crash bin from the fuzz on Trillion, and you can see that there was these are all the fault points and the test case numbers that cause faults at that point. And so one of the cool things that we can do with this next is we can graph this thing. So you can't read it, but I'm adding a -G and whatever, just test. So I'm going to create a graph, and I'll start that up. It's being rendered in UDraw. And so this graph shows all the fault locations, just like the crash bin did, but it pulls on the stack back traces to kind of pull it back to a single fault place. So we had 3 faults that occurred at this address, 2 at this address, 24 at this address, and 1 at this address. But because we can see it in this graph format now, we can go up and we can see they actually all started from the same location. And this actually was very helpful because it's not that I found 30 different bugs. It was a single bug. It just kind of presented itself in different areas of the binary. So, again, not to pick on Codenomicon, but when we were doing one of our first VoIP tests with it, we had something like 2,000 crashes. And it was 1,996 crashes because of one format string that was really, really low level and was getting hit all over the place. And then it was 4 other issues. So we had to go through each one of these things to make sure that we weren't missing a bug. And because we're not the developers, we can't just fix the problem and go retest. It was really painful, and I'm sure my guys hated me for it. But so now if you have this kind of tracking, what we would have seen is just 4 paths, 1996 faulting on one position, and then 1 for each other fault. Oops.
So the next utility is we call it the IDA fuzz library extender. This is an IDA Python script, and what it does is you run it from within IDA, and it's going to rip out all static comparisons. So if it's a compare register immediate value, it's going to rip that out. If it's a string compare, so I go through and spider all the Y character string compares and all the other random string compares that are part of the Win32 API and others, and it takes all of those and adds them to 2 files in the root Sully directory. So when you actually start fuzzing, it will the fuzz library for integers and strings, it'll append all the values that this enumerates for you into the fuzz library. So it's kind of like, it makes it a little bit smarter. And this has helped in a few situations where there's a magic value that you haven't found through reversing yet. This will be able to pull that out, and it'll actually add it to the library, so you'll have a better chance of actually hitting that and passing certain tests. I'm going to do a quick demo of it.
I'll just run it real quick.
Yeah. So this is the HP bug, which still isn't.
This is IDA. This is an IDA Python script. You launch it, you tell it where you want to save it to. And one of the benefits of having this is, let's say you want to add target-specific strings and integer types, but you don't want to extend the library. You just want it for a certain target. Well, you can save that .fuzzstrings, .fuzzint only for trillion or only for HP. Kind of pull it off into the archive fuzzies when you're done with it.
Right, and you'll see here, these are all the integers that it discovered, and these are all the strings. As you'll notice, there are a lot of nulls, which is Unicode, because most of this process deals with Unicode, and therein lies the bug, actually. But some of these values are actually useful. They're the magic values that you need to actually get through and pass certain checks.
Yeah. I'm going to skip this PCAP cleaner. We'll skip this one. All right, so we're going to do 2 demos. You can do your HP one first.
All right. First thing we're going to do is a bug in Hewlett-Packard Data Protector. So we already have the image set up. Okay, so this is VMware image with the software installed. We have an installer for Sully. I'm just going to show you the first page of it. I'm not actually going to install it because I've already done so. But it's just a nullsoft scriptable installer, really easy. Yes, go away.
It's probably the number 1 complaint I got about PyMay is that installing it is a pain in the ass.
Which is why I wrote that thing.
So now my response was, I don't care.
Right. So now we're going to go into the Sully directory itself. Maybe. Okay. Going to fire up the network monitor, which is going to save all the PCAPs for everything we're doing here. And we're going to start up the process monitor and attach to the process that we want to deal with. So the process monitor is going to take a crash bin file name. I'm just going to call it HP. Process name, in this case it's on the iNet. And we're going to set it to log level 5. So now that's going to sit there attached to the process and await requests. Next thing I'm going to do is the network monitor just to sniff all the packets. Choose interface number 1. Filter is going to be source or dest port 5555, log level 5. Okay, so now everything is set up here.
Switch back to that one real quick. Let's just make sure it's on there. Cool.
Yep, looks good. At this point, I'm going to take a snapshot of this VMware image so that if a fault does occur, it's going to revert back to here, so we'll be good to go again. So we're just going to take a quick snapshot, call it Slowly good to go. Okay.
And on this whole health restoration thing, so this was just a typical problem. Like, let's say you wrote a Spike script and you want to run overnight, find you faults. Well, maybe 2 hours into your sleep, it would have found a bug, and then it just stops. It just sits there. So what we want to do is we want to take advantage of all those nighttime hours. We want to constantly be fuzzing. So in the event that you do have a virtual machine control, it will revert to that known good image, and obviously it's restored to good health. If you don't have that, but you've got the PyDebug control attached to it, it can restart the target service. So you can give it optional arguments like netstop x, netstart x. And of course, if neither one of those two are available, we can fall back to the ultra crappy, just wait for it.
Okay. So now that that's all set, it's running. Power that down. Okay. Now we're going to run the VM control. And this, I guess I'll show you guys. It's just the interactive mode, which lets you do this fun stuff. You just need to point it to your VMware directory so that it, I can't see. There we go. And to your image itself, which I'll just do over here. In a minute.
Yeah. So the virtual machine control is outside of the environment. The PyDebug has to be inside. The network monitor could be either. Currently, in this case, we just put it inside.
All right, then you got to give it the snapshot name where everything is good. So we're going to call it good to go. And the log level. So now this is ready to go. And we're going to fire up our driver script, which is Fuzz Data Protector. So while that's going, I'm going to quickly show you what that file looks like.
Show the web interface real quick, too.
Okay. The web interface. This will come up once once everything attaches here.
Yeah. So what's going on is it's going to instantiate VMware through VMrun, which can take a little while, and then it's going to all the stuff is synchronized. It's just the fuzzer's waiting for the image to come up, then it's going to wait to get a ping back from the debugger and the net monitor saying everything is good, and this is going to start fuzzing. It says, okay, guys, test case number 1 is coming. So netmon, you need to start recording. Procmon, you need to start recording. The code coverage monitor, you need to start recording. And then if there's a fault that comes back from the PyDebug script, it can say, okay, VMrun, you need to restart, or...
No, that's not. That's from later. That's from earlier.
Is it not coming up? Oh, demo gods.
Yeah, I knew this was going to happen.
Well, let me do mine real quick then. Oh, wait, is it working?
Let me just kill this and restart it.
The laptop respects me. Let me get my hands on it. It knows who it belongs to. While that goes on, we can just show this, which is...
Yeah, this is the actual... that's the driver, which you just set up the session, you point it to the actual process and the port and all that, and set up your agents. And this itself is the actual protocol. I just wrote a quick little custom encoder, which is that Unicode function right there, which just splices in nulls to whatever string that you give it. And here's the actual protocol. So it has one packet, which is it's just one packet just telling the process the size of the following packet. You got to restart those. Which is why we use the sizer for that part. So it's just a sizer saying the next packet is going to be the size of block number 2. And block number 2 is where the actual protocol is defined. And this protocol is fairly simple. It's just going to be a byte order marker in Unicode, which is FEFF, and then it's going to be a few Unicode things. You just have to give it a few Unicode numbers to pass checks to W2I functions. And if you get by a few of those, I think there's 3. There's one magic value, which is a D word, which is the IDA file fuzz extender will actually pull out for you. And the last thing that you do is just a huge buffer, which overflows a wide character string copy. And this process itself probably has about 15 more bugs in it that I haven't actually tried to fuzz out. So... happy hunting.
Where's the hammer?
Yeah.
If this doesn't work, I'm smashing the laptop. There we go.
There. All right, now it's working.
So it's restoring the...
So the VM control is starting back up the image to the good to go, and the fuzzing should be starting. If you go back to the console, you'll see it.
Well, yeah. So you can kind of see the debugger thread just kicked off, and there, this was just informed, hey, you need to start recording. And then the fuzzer is starting to transmit. So it'll tell you the current path, what it's sending, how many bytes are captured, etc. And now you can kind of see this web interface. Oh, we forgot to, of course, clear out the session. So,
well, this is our previous session. You'll see that there's some exceptions shown below. Those are from our testing previously, and I didn't clear out the session file, so it's just resuming where I left off. But you'll see that there's invalid 33333, so that's EIP, so it's a Stack Overflow, smashed a bunch of stuff. You click that, you'll see the context data. Gives you a ridiculous stack, and the SEH unwind is at the very bottom of this.
Yeah, the process is definitely not happy.
Yeah, this thing got screwed over pretty badly. I mean, you can basically copy the entire size of a packet that you could possibly send over the wire into a, I think it's like 268 byte stack variable. So you can smash stuff pretty well in this.
So this will, the nice thing about this is now we can just leave. Like, we'll set this up on a Friday afternoon. We'll leave for the weekend, and when you come back, it's gone through everything. It's exhaustively recorded every single packet capture. It's recorded every single crash, and it'll tell you, what it's gone through, where the faults are. It's got the crash bin, so you can explore it with a graph. All these other aspects.
That's definitely the beauty of it, that it's completely autonomous. So you set it, say go, exceptions will occur, it'll revert, it'll continue. And if you don't have VMware and you don't have the latest version that has that API exposed, you can use our process monitor. Process monitor has certain options that you can say, if it's a service, for instance, on Windows, you can actually specify in the process monitor option, say, to restart this service, do net stop this, net start this. It'll restart the service rather than using the VM control. So it's really your preference, but the cleanest way to do it is the VM control if you have that option.
All right, let me just switch it over to my trend demo, which hopefully will be a little bit smoother. Can you switch these drives while I go over this stuff? So the trend demo is a little bit, it's a better example because it's a little bit more complex, so you can kind of see some of the better features of the fuzzer. So because it's a DC RPC, it's a RPC endpoint. So you can see in this driver script, I kind of defined it a little bit more. Because it's freeform, I had two options. I made it so I can send a single request or it would be the full fuzz. And in this case, we have, it's only single deep, so the root node is going to connect to these, 6 different requests that I have set up. This stuff all looks familiar. And then here is the RPC bind pre-send that I have defined. And so this utils.dcrpc.bind is from Sully. And all it's doing is saying, okay, set up the RPC interface because then the data is going to be coming afterwards. You got to change the driver.
Change driver paths. Yep.
1 second.
Enter.
And so here's the actual request. So I'm setting up in this case, I'm using this is the benefit of having it in Python. I'm generating 6 different requests, but I'm doing it programmatically. So I'm saying for every operation number and submax. So the way that the trend protocol works is that you've got an opcode, and then each opcode has a certain number of subcodes. So I reverse that out, and I put it in here. So opcode 1 has 22 subcodes. 2 has 19, 3 has 85, etc. So for every one of those, initialize a new request where the name is the target port and then op number. Then create this new block, which the encoder is an RPC request encoder. Again, it's built into Sully, so you don't have to worry about defining all the RPC types. You just worry about string, data, whatever. And then here comes the request number. You can see here I'm using Python's map functionality to automatically generate this group. Arrow would love that line of code, my map car here. And some standard things. There's a string, a sizer, the block ends, all this jazz. So
we have simpler examples. If you want to get going and you just download this, there's an entire request library that we have right now that has basic stuff like HTTP and a few others if you just want to get a feel for it, rather than having to do all the crazy encoding and stuff like that, which is a little daunting at first.
Here's the VM control. And I've already done this whole snapshot thing where there's a snapshot of the netmon and the procmon running. So I'll just say, fuzz trend. And this should come up with a nice clean session. So here's the virtual machine control. It got the request from the fuzzer saying, okay, it's time to bring up the virtual machine. And one of the nuances of the VM run command is that you can't intermix manual VMware with automated VMware. So if you started VMware, VM control can't play with it. You have to stop VMware and let the VM control deal with it on its own.
Which is why my demo kind of froze for a second there. Because what I would have had to have done after setting that snapshot is just close VMware and then let the VM control itself start it up, which is what this is doing right now.
So it's restoring the virtual machine state, and then it's going to start fuzzing. And when it does, we should have a nice new fresh web interface. So this is coming up. You can see the procmon and the netmon. They're getting invoked. Now it's saying, hey, start testing. And I skipped it forward to 36 because I know that there's a fault at 42, just so you can kind of see it happen in real life, and it better happen. Here, there it is. You can see it already caught it. It's restarting the virtual machine. It was a 40, not 42. So it caused a fault. Obviously, this is exploitable. And it's got everything saved, and now it's going to restart the virtual machine to a known good state and then keep running. And so this restarting is actually really important. We were fuzzing Veritas something or other, and what had happened is originally I was just using the process control to just stop and to restart the service because it's obviously a lot faster than VM control restarting. But the problem I was hitting is that one of my fuzz cases was setting some registry option that was actually causing the fault. So it was an infinite CPU usage in Veritas because of some registry key that my fuzzer was able to create. So even if I stopped and started the entire OS, it was still going to default to a full CPU lock. So this is the benefit of having a VM controls, that you can go all the way back and make sure that you have a known good state. And you can see this thing is just working completely unattended. We can just sit here and it's actually really fun to watch. You just let it go, run, and it's doing all the work for you. If I wanted to, I could pause it, resume it, all that jazz. Are there any questions thus so far? Yes, no? Before I jump into the future stuff.
On your random types,
Mm-hmm.
can you kind of inject a value to it on the replay? So if you've got a fuzz case where you've gone through, you've found the burden, you want to either instrument it more, or an exchange code, if you're still working on that, can you then replay your fuzz with the same values that were previously used random?
So the question was, we're generating all this data, right? And it's deterministic. So if I have strings, integers, etc., if I run through the whole fuzz session and I run through it again, because the data is generated on the fly and it's deterministic, it's going to be the same. But the question is, well, how do you deal with that with random data? Because it's random every time, what if you want to replay one? Well, that's where the PCAPs come in handy. Because if I saw that a certain test case caused the fault, I can go pull up the PCAP, I can look at what that actual value was, and then swap it from random to static to replay it. So that's how that is handled.
And not only that, you could rip it out, and instead of a random, you could change that to a string and add that actual value to the string fuzz library. So it would be another magic value they might want to work with.
So we have just a couple minutes left. Let me quickly go through some of our future stuff. So these are things that are nearly done. And when I say nearly done, I mean they're finished but just not ready to kind of give to you guys. The parallel fuzzing we were really proud of, but broke it last week. So I pulled that code out, and right now you can only add one target, although you'll see you have the capability to add many. So I just pulled the splitting algorithm out because we had broken that. Another really cool thing we have is sequence honing. So for any of you who have fuzzed before, I don't know how often this has happened where, let's say we have test case number 100, it generates a fault. We go back to replay 100 and we get nothing. So, it's not like the world has changed. It's because there's probably some subset of sequences beforehand that set up that vulnerable environment for 100 to come in and do its dirty. I gotta kill this thing. Hold on 1 second. So, oh no. There we go. So what we can do is because we have all these components built in, we can write a really easy script to kind of hone down what is that set of test cases. So here's the first, whatever, quote-unquote, algorithm I came up with to do it. I start from the last test case that caused a crash, and I start stepping backwards. So send 100, doesn't cause a crash, cool. Send 99, 100, no crash, 98, 99, 100. And you keep doing this until you find the final window. So maybe sending from 40 to 100 is what's going to cause a crash. So we know that somehow 40 is involved and 100 is involved at this point. Then we start eliminating sequential bundles from this range. And the bundle size is a ratio of the window size. So, in this case we have a range of 60. Maybe it'll start eliminating 2 at a time. And it'll resend the whole sequence with those eliminated, check for a crash. If there is still a crash, it'll start eliminating more and more. And so in the end, you're going to end up with the final exact sequence. Like if you send 40, 45, 95, 99, and 100, it's going to trigger this crash. And this can take a long-ass time, like a long, long-ass time. But it's way, way easier than manually doing it on your own. And you have time, and it's all automated. Like, you just set it up, and you come back a week later, and it should give you the exact, sequence. So we mentioned the parallel fuzzing. The heuristic feedback loop, this is the more advanced version of that IDA fuzz extender, which is really simplistic. So what we're going to do is we have code coverage. We're like watching everything. We're single-stepping through. It would be nice if the current primitive that's being fuzzed has gone over an area of code that has an integer comparison, for example, and we're dealing with an integer. The feedback loop will send it back to the fuzzer and add it to the integer library for that specific primitive. And so there are way more scientific ways of doing this. Both Greg Hoagland and Halvar are working on what I call path math, where you can say, okay, if I'm here and I want to go here, how do I generate the inputs mathematically so I can force this execution? Neither one of them have finished it yet, but in talking to a friend at Microsoft, apparently they already have it, where their fuzzers are capable of fuzzing every single code flow. So I guess we don't have the coolest fuzzer on the block, but we have the coolest free fuzzer on the block. Code coverage monitor is done. Oh yes, we didn't bundle it because it adds a lot more requirements. So the installer would have to actually include PyMA, and I don't have a PyMA installer, but now I have an installer guy, so Aaron's going to be creating one for me.
Maybe.
Another idea we had is PCAP binning. The same way that we can bin crashes, we want to bin PCAP. So if you're fuzzing a router or you just don't have the option to put a debugger into it, it'd be nice if we can just look at those responses and categorize those as well. So a simple example, we're fuzzing a web server, 404 responses versus 202 responses. Or like if you're fuzzing the Xbox, for example, which we've done with Sully, you can do this PCAP binning. File fuzzing, although we've designed this really for network protocol fuzzing and the session is specific to that, the data generation is really global. So Peter Silverman's already written a beta replacement called file session. And also, alternatively, you can just do this data generation and loop through the .render call, then take all these generated files and just plug it into Cody's file fuzz and use that as a testing harness. So you can do files with this as well.
It just returns the raw data, so you can do basically whatever the hell you want.
And the last thing I wanted to mention is that we may create a web GUI for drag and drop blocks, put primitives on it, right-click, pull up the dialog box, set the options, all that crap. And then what would be really nice is if then we just made an appliance-based distribution. So it'll just be a VMware image. You download it, no install required. It's got a web interface. You connect to it, you design a request, save it to the library. Do another request, save it to the library. Create a new session, tie them together in an interactive graph, add some targets, and start fuzzing. And it's all doable because I see it in my head, I just don't see it motivationally to go out and do it. So it would make this a lot easier to use, but it's not going to make it any more powerful. So we just now hit the time limit. But are there any questions? Sure.
I was wondering how you said before you can bring in Wireshark XML packet. Is that an exception to setting up a block-based deal? Or?
No, it's not. So the question was, what do we do with these PDML files, right? This PDML file, we just parse it, and instead of you having to copy-paste hex bytes, it's just going to save you some time, because it's going to say, here's a block, here's a string, and depending on how well Wireshark knows that protocol, it's going to do a little bit more, a little bit less work for you.
And even in unknown protocols, I built in a little bit of heuristics with it, so it'll kind of look for ASCII, and if it's ASCII, it'll define it as an S string rather than an S binary and stuff like that.
And that's getting smarter as we use it more. There were some other questions. Yep.
Do you guys have a provision for multi-tiered applications where you need to monitor multiple machines, multiple processes?
I haven't done that. That's actually really interesting where you're fuzzing one thing. Oh, the question was, do we have anything for multi-tiered applications? So if you've got two systems and you're fuzzing one and the other one breaks, it would be very doable. I mean, you can have multiple agents. It's just adding a new feedback loop, right? Where instead of checking one, you're checking both. But
we're working on an agent API that'll make it really easy for you to add another agent, so you can very easily do checks like that if you needed to.
But I mean, all the components are there, so it's just a matter of building the logic in. So that sequence owner, it took me, a day to come up with a good way of doing it, and 10 minutes to write it, because all the tools are there. There were some other questions. Yep.
So I was wondering whether you can actually, using your block modeling, read data from targets, and basically parse it using your blocks, but you can, for example, manage the study.
So the question was, can you just read data, make it a block, and do man-in-the-middle fuzzing? It's a good idea, and it's something that we've tinkered with. Actually, Cody has written a proxy fuzzer, and it's a lot more simple than that. What it does is just sits in the middle. Anytime it sees a string, it'll expand it, it'll remove it, it'll put some crap in there. Anytime it sees an integer, it'll do stuff with it like that. But that would require that we parse that would require some protocol informatics stuff, right? Where you've got this big blob, you've automatically broken it out into fields, and then you're fuzzing those fields. So, yeah, conceptually, it's cool. Have we done it? No. Will we do it one day? Maybe. It's interesting. Somebody else had a question in this general area? Yep. So the question was, if I've written a fuzzer in Scapy, will it automatically convert it to Sully? Do I look like a commercial vendor shop? It doesn't do that, no. You're going to have to convert it manually. One thing that we have done along those lines is we've made a Spike compatibility layer. So if Spike's got these long-ass names like S-Sizer, half-word, Intel, binary, x86, on like Valentine's Day. So we've made aliases for those that'll call through to ours. And we haven't completely finished that, but for the most part, converting a Spike script to a Sully script should be very easy. We haven't looked at Scapy yet, though. So, sorry. Any other questions? Yep.
Yeah, I'd like to answer your cross-platform. What about the integration with VMware? Is that particularly tight or like Zen?
You would have to, does Zen have a external automation? Yeah, you can. You'd have to create a new agent. The other thing is... Okay.
I was going to say, that'd be pretty easy. You can almost rip a lot of the code right out of the VMware agent and just make a Zen agent, and it's really easy. And we're really working on simplifying the API, so you can do that very simply.
So this whole cross-platform notion, yes, it's Python's cross-platform. VMware runs on Unix, so this would work on there too. But obviously we're very Windows biased here. We don't have a Unix debugging agent. We have a Windows debugging agent. But for the most part, everything else should work across platforms. And Charlie, who's sitting behind you, is working on a Mac OS version of PyDebug. So when that's done, it'll be, we'll have a debugger for Unix world as well. Yep. I thought we were done. Cool. So we still have time to take questions. Anybody else?
He had a question earlier. No? Answered? Okay.
No other questions? Last call. All right, yep.
So how do you deal with protocols such as Lime? There's several layers of requests for Lime, setting up a couple layers of protocol before you do something else.
So,
In order to do that all with reconnect, assume that you're not going to fuzz those layers, just do it one at a time.
So it depends on your goal. So in the case of Trillion, I didn't want to fuzz that initial, right? There was only one, so we did a presend. The question was, how do you deal with multiple layers of transmissions and receives before you get to the part that you want to fuzz? If you want to fuzz it, you define all those different requests, and you just graph them together, and it'll go through everything and fuzz everything. And if you want to, you can skip forward 1,000 cases and start fuzzing another area, or you can just statically put it in the pre-init, but it 100% does handle that situation.
That's the beauty of sessions. You can make this obscenely complex session and then skip mutations all the way down to right here and start. So if you didn't want to even deal with any of that, you could just skip it.
Cool.
I think we're done.
All right, guys, well, if there's no other questions,